So let me give you another Markov chain. We'll represent it by this transition matrix. It'll be a 3 by 3. It'll be 0, 1, 0, 0.4, 0.3, 0.3, 0, 1, 0. So this will be the transition matrix for our Markov chain. And I'm going to ask us to find the stable vector. But I might ask, first of all, is this a regular Markov chain? How would I know? I can't conclude immediately that it's a regular Markov chain because there are these zeros. And so it's not immediately obvious that it's actually regular. So just to be a little nitpicky, we might want to check if it's regular. And I'll just tell you that if you take p squared, you get the following matrix. I won't harp on the calculations. You can check this yourself. But you should get this matrix if you take the square of that p. Like so. So already at p squared, I see that all the entries are positive. And so I'm done. This is a regular Markov chain. So it is regular. Because all the entries are positive once I take p squared. So remember, to be regular, I just need all the entries to be positive after some power. Some power. In this case, that sum is 2. 2 is the power I need. And then every power after this will also have positive entries. So this is a regular Markov chain. Okay, so if you like, check this calculation yourself. I'm not going to bore through the details up here. Okay, so now we know it's regular, so it really does have a stable vector, so I better find it now. So let's find the stable vector. And we're just going to do just like we did before. We're going to set up the equation. We have w p minus I equals 0. So what's w times p minus I? Well, w is just w1, w2, w3. And p minus I, make that a little bigger. P minus I is p minus the 3 by 3 identity matrix. And so I'm going to take 0 minus 1 to get minus 1. 1 minus 0 is 1. I'll get 0, 0.4. 0.3 minus 1 is minus 0.7. 3, 0, 1, and then negative 1 again. So to get this, I'm just subtracting the 3 by 3 identity matrix from this. So we might just recall, again, the 3 by 3 identity looks like this. 1's on the diagonal. So I subtract these two guys to get this. Okay. So now I'm just going to carry out this multiplication, and I'm going to set it equal to 0, right? So setting this equal to 0. So every time I multiply this by a column, I have to set that equal to 0 to get my system of equations. So of course, before I do that, I always include this equation. W1 plus W2 plus W3 equals 1. I always have to make sure I include this equation. So I'll just throw it in there first so I don't forget. And now I'll start carrying out this multiplication to get the rest of the equations in the system. So I'll take the row times the columns. And just like before, I can ignore the last column, because if I take all of them, one of these is going to be a redundant equation. I don't need it. It won't tell me anything new. And so I'm just going to ignore maybe the last column. And that'll work. So let's do that. So we'll take this times the first column. We'll get negative W1 plus 0.4 W2. And I have to set that equal to 0. And then I'm going to get W1 plus minus 0.7 W2 plus W3 and set that equal to 0 as well. And then I'll just ignore the last column, because again, that will give me a redundant equation. Okay, so here's my system of equations. So again, this is always going to work out so that you'll have this one, and then all the other ones will just be something set equal to 0. So it should always be like 1 and then zeros, and we're set equal to in every one of these examples. But now we just have to solve the system, and it will tell us what the probability or what the stable vector is from here. So let's write down the, this is a system of 3 equations. I don't want to do substitution or anything like that on a system of 3 equations. let's use matrix methods. Let's set up the augmented matrix and reduce it. So the first row will be 1, 1, 1, 1. So basically, every time you set up the augmented matrix, your first row is just going to be 1, always, in this situation. Because I'm always going to have this equation. So my first row will just always be all 1s. And then the other ones depend on the matrix, the transition matrix. Here I'm going to get negative 1, 0.4, 0, 0. And here I'm going to get 1, minus 0.7, 1, and 0. Okay. And so now my goal is to reduce this. So I might go ahead and just, this is pretty convenient. I have 1s everywhere. So this is not so bad yet. I'm just going to add the first row to the second row to cancel out the negative 1. That's row 2 plus row 1. So what's going to happen? I'm going to get 0. I'm going to get 1.4. I'm going to get 1. I'm going to get 1. And while I'm at it, I might as well get rid of this guy too. So I'll also subtract the top row from the third row. So 1 minus 1 is 0. Minus 0.7 minus 1 is minus 1.7. And 1 minus 1 is 0. And 0 minus 1 is minus 1. Okay. And then 1, 1, 1, 1. So this will be my new matrix after these two steps where I've canceled both of these guys. I just kind of did it in one move here to save myself some writing. Okay. So now the first column is good. I need a 1 where this 1.4 is. So the good idea would be, basically my best move here would be just divide the second row by 1.4. So just divide by 1.4. That feels kind of, it never feels good to divide by a decimal. So for me, it's helpful to convert to fractions. If you're doing this out by hand, it's useful to convert to fractions. What's 1.4 as a fraction? Well, it's actually 7 over 5. So when I divide by 7 over 5, I'm really multiplying by 5 over 7. So if I want, this is really the same thing as 5 over 7 times row 2. So what I'm going to get is 0, 1, because I'm just dividing 1.4 by itself. And then 5 over 7 times 1 is 5 over 7. And again, 5 over 7. And so here's my matrix. So I have a 1 here. I have this leading 1 here that I want. Now I'm going to use it to kill these guys. I need a 0 here and a 0 here. Now, getting the 0 in the top row is easy because I have 1 and 1. So I'm just going to subtract